Hello everyone, welcome to the 17th video of our lecture series. So in the previous video, we are talking about time independent non-degenerate perturbation theory. So let us briefly recall this. So we have our Hamiltonian to be H0 plus HP, where H0 is our Hamiltonian of exactly solvable system, and HP is our perturbative Hamiltonian. So we assume HP to be of the form lambda W, and we assume also that HP will affect the energy spectrum and energy eigenfunction by only a smaller margin. So since H0 is our Hamiltonian of exactly solvable system, so we already know the eigenstates of H0. So let us denote those by psi n. So if psi n is the eigenfunction of H0, we can write H0 psi n to be En 0 psi n. So this is the eigenfunction, this is the eigenvalue for the corresponding eigenfunction psi n of the operator H0. And now we want to solve this H. What will be the eigenfunction and eigen values of H? So it is, let us assume this En psi n. So in the perturbative analysis, we assume En to be En0 plus, we assume the series form of lambda. So lambda En1 plus lambda square En2 and so on. And we also assume psi n to be phi n plus lambda psi n1 plus lambda square psi n2 and so on. So from the analysis that we have done in the previous video, we have found the value of En1 to be phi n W phi n. So this is our correction term in the energy up to first order of lambda, and we also find the correction term in the eigenfunction up to first order of lambda to be so first order correction will be summation over m, and f should not be equal to n, and we have phi m W phi n divided by En0 minus Em0 phi m. And we found out the second order correction in the energy to be En2, which will be equal to m not equal to n summation over m phi m W phi n squared divided by En0 minus Em0. So this is the result of our time independent non-degenerate perturbation theory. So now what will be the case if we have an unperturbed states which are degenerate? So suppose we have two or more different states which share the same energy. So we have two states, suppose two, or it can be more, two. So we have to have at least two. So two different states So let us assume them to be psi m and psi L. So this is our two different states which share the same energy. So that means so same energy, then our ordinary perturbation theory will blow up. So basically these two states, if we apply our energy unperturbed Hamiltonian H0 on these two states, then we the eigen value, like this eigen value will be same for both the states. So in that case our ordinary perturbation theory will not work. So why? So suppose let us see why it will blow up. So suppose we have our initial state to be phi 2 and we have to calculate the second order energy correction in phi 2. So that means we have to calculate E2 energy correction in the second eigenstate in the second order. So this represents order and here this represent in which state we are doing the energy correction. So then what will be E22? So then according to this formula we will have E22 to be summation over m and m not equal to 2 and we have here phi m w phi n and squared divided by E2 0 minus EM0. So now this summation of m, it is over all the energy eigenstate. So now suppose we have another eigenstate, let us say phi 9. So we have phi 9 and so another eigenstate phi 9 which is degenerate with phi 2. So phi 9 and phi 2, these are degenerate. So that means the energy value of the unperturbed state phi 2 will be equal to the energy eigenvalue of the unperturbed states phi 9. So whenever we will do this summation over m, so for m value, when m value will be 9, here we have E20 minus E90. But since these two energy values are same due to degeneracy, this term will lead us to 0 and our E22 will blow up. Or it will diverge. So simply our non-linear perturbation theory fails. So now we have to find an alternative way to tackle this degenerate degenerate eigenstates. First, let us proceed with twofold degeneracy case. So we have two eigenstates which are degenerate. So twofold degeneracy. So what does the twofold degeneracy means? So it means we have two eigenstates which are degenerate. So this is our first eigenstate which is one of the degenerate states, and here we have second eigenstate. So since these are degenerate, the energy values will be same. So it will also be EM0 phi L. And these states, this phi m and phi L, they are orthonormal. So this will be 0. So since this phi m and phi l, these are eigenstate of H0, so any linear combination of them will also be an eigenstate of H0. So any linear combination of phi m and phi l will be an eigenstate of H0. So let us suppose this combination to be of this form. So we have two random coefficient alpha and second one is beta. So this phi, it is an eigenfunction of H0 because so whenever we will apply H0 on phi, so this will give us the energy value EM0 and this will also give us the energy value EM0. So we can take the EM0 outside and we will have EM0. Here we will have alpha phi m and beta phi l. So this will be equal to EM0, we have phi. So this phi is an eigenstate of H0. Now what will be the case if we have perturbation? So if we have perturbation, then it will break the degeneracy. So perturbation, so it will break the degeneracy as we increase the lambda from 0 to 1. So if we want to express this in graph like this, so it will be like that. So we have our lambda value. So this is our value 1, this is our lambda value 0, and this is our EM0. So for lambda to be 0, we have our Hamiltonian to be unperturbed and both the state will have same energy value. Now as we increase lambda, it will the degeneracy will be lifted and one of the state will have energy value will go energy like this and other state will have energy like this. So in this way the our degeneracy in the two state and that will be lifted as we increase the value of lambda. So now if we go in other direction, that means when we turn off the perturbation, then the upper state, this one, it will reduces down to one linear combination of psi m and psi l, and the lower state it will reduces down to some another orthogonal linear combination. So when we turn off the perturbation, the upper state will reduces down to one linear combination of psi m and psi l, and similarly the lower state will reduces down to some orthonormal linear combination. But we don't know a priori what these good linear combinations are. So for that we can't even calculate the first order energy correction because we don't know what will be the unperturbed states to use. So that is why we need to rebuild its theory completely. So now let us just write the good linear combination as we assumed before, like this. So we have our state psi to be alpha phi m and beta phi l. Now we want to solve this equation. So we have H, it will act on psi and it will give us E psi. So here what is H? H is H0 plus lambda W. We have our E to be EM0 plus lambda EM1 plus lambda square EM2 and so on, and we have our psi to be phi plus lambda psi 1 plus lambda square psi 2 and so on. So if we plug this equation, if we plug this psi E and this H here, and we similarly like the previous video, we just collect the terms of lambda up to first order, second order, then we will get at first order. So at first order we will have our equation to be H0 acting on psi 1 plus W acting on phi, and here in the right hand side we will have EM0 phi 1 plus EM1 psi. Now if we take inner product of this equation, so inner product with phi m, so what we will have? So we will have phi m H0 psi 1 plus phi m W phi, and here we have EM0 phi m psi 1 plus EM1 phi m psi. Now since H0 is Hermitian, so this phi m H0, it will give us EM0 phi m. So if we notice this term and this term, so they will be same, because this term will give us EM0 phi m psi 1, so which is same as this. So these two terms will cancel out and we will have, so this phi m psi, it will give us phi m, here we will have alpha psi m plus beta psi l, so it will give us just alpha. So from here, from this equation, this one, from this one we will get E1 product with alpha. This is our right hand side, and in the left hand side we will have alpha phi m omega phi m plus beta phi m omega phi l. Yeah, so this is a getting. So this is our energy correction in the first order, of our degenerated states. So since so let us for simplicity drop this, we are dropping this m term now. So we will have E1 alpha E1, which will be equal to alpha. Now these are what? These are matrix elements of our perturbative Hamiltonian. So we can denote this by W mm plus beta W ml. So these are just the matrix elements. So similarly, if we take inner product of this equation with phi L, so now if we take inner product with phi L and do the calculation similarly, then we will get beta E1, which will be equal to alpha omega Lm plus beta omega LL. Now if we multiply this, so multiply with ml, and we use this equation to eliminate, so and use, so let us denote this by 1 and this by 2, and use 1 to eliminate beta omega ml, then we will find the following equation. So you can do this, it is just simply easy, it is easy. You have to multiply and take subtraction. So we will end up with alpha omega ml omega Lm minus E1 minus omega mm and E1 minus omega LL. So this will be 0. Now this 0 means we have two possibility. Either we have alpha to be 0 or we have this to be 0. So for degenerate case we have alpha to be non-zero. So if alpha is non-zero, then we must have this term to be 0. So if we arrange this term properly, we will get E1 square minus E1 omega mm plus omega LL, and we have here omega mm omega LL minus omega ml omega Lm, this to be 0. We know that this Hamiltonian H0 and Hp both are Hermitian. So for that we have omega Lm to be equal to omega ml star. So if we have this condition, then from this equation we will have E1 plus minus. So since this is a quadratic equation, it will have two roots, and the roots will be half Wmm plus WLL plus minus root under Wmm minus WLL squared plus 4 WML squared. So this is the fundamental result of our degenerate perturbation theory. So these two roots, this corresponding to the two perturbed energies. So now for the side note, now let us suppose if we have alpha to be 0, then we have beta to be 1, and from 1 we will have WML to be 0, and from 2, so from 2 we will have WLL to be E1. So if you notice carefully, this one is included in this general result with the minus sign. So now let us calculate E1 plus and E1 minus. So E1 plus, it will be half WMM plus WLL, and for plus we have here this, and for non-degenerate case we have this element, this cross element to be 0. So here we will have omega mm minus omega ll. So this is equal to omega mm. Now similarly, omega 1 minus, it will be half WMM plus WLL minus, so here we will have minus, so minus omega mm plus omega ll. So it will simply give us WLL. So if we notice carefully, so this is precisely what we have obtained using non-degenerate perturbation theory, because this WMM, it will give us phi m omega phi m, and this WLL, it is phi l omega phi l. So our non-degenerate case is already included in this degenerate case, because for non-degenerate case we have either alpha to be 0 or either beta to be 0. So for both the cases we will have this cross terms to be 0, and if we calculate the energy eigenfunction, if the cross terms are 0, then one root will give us WMM and another root will give us WLL. So this is first order correction in the energy of the mth state and nth state. So now we are set with the theoretical details of both the degenerate case and non-degenerate perturbation theory, obviously time independent. So we will in the next videos or next few videos we will solve the non-degenerate time independent and degenerate time independent perturbation problems. So from next video, we will solve some problems on time independent, degenerate and non-degenerate perturbation theory. And after we are done with some problems, then we proceed with our time dependent perturbation theory. So that's it for today's video. So we will meet on our next lecture video.